Oh my, excuse me. Hello everybody and welcome back. We're still looking at the 2014 Canadian Open paper, the COMC. We're on the very last of the short answer questions. We are on B4, so we do just need to give our final answer, and that's that. But we will show our work, especially because I find B4 is one of the harder questions on the paper, even though it comes before all of Part C. But things like, C1 is never particularly bad, neither C2 I find. I would say in terms of difficulty, C4 hardest, then C3 sometimes, B4 some other times. B4 and C3 can swap places, I find, in terms of difficulty. But B4, not something to sneeze at. Definitely a difficult question, I expect. Well, let's see. Let f of x be 1 over this cubic polynomial. Yikes. Determine the smallest positive integer n so that if I take f1 plus f2 plus f3 all the way up to fn, add them together, it's greater than 503 out of 2014. So that's roughly a quarter. Roughly a quarter we need to be bigger than. Okay. So, for a question like this, I would strongly recommend that you don't, you can look at small little numbers and plug them in, but the questions like this have popped up every now and again. And you'll find that it can be kind of tedious to actually write out each term and add them up and things like that. You want to look for patterns, and the question I'm always reminded of when I see an expression like this, I always think partial fractions, not only because I teach calculus 2 every once in a while, and that has a lot of partial fractions in it, but I always remember this one question where you're sort of asked to sum up the numbers 1/2 plus 1/6 plus 1/12 plus 1/20 plus 1/30 plus 1/42, and you can make it go as high as you want. And the thing to realize is, how are we making these numbers? Well, each of these numbers looks like 1 over and then a product of consecutive numbers. And you might say, okay, well, so what, root beer? What's going on with that? Well, there's a nice way to write these numbers in that they're 1 over 1 minus 1/2 plus 1/2 minus 1/3. You can check 1/6 is a half minus a third. 1/12 is a third minus a quarter. And if you bother to write it out this way, lots of things cancel, and so to add up the first 4 terms, to add up these first 4 terms, is really the same as adding, well, what's left over? 1 over 1 is 1 minus a quarter, because everything in the middle cancels. This is what's called a telescoping sequence. And so if you learn to write things in a different way, learn to write something like this in a different way, terms might cancel. I'm not guaranteed that that's what's going to happen here, but I strongly suspect it is. Okay? This is based off experience that I am now passing on to you. So let's look at what they've got. It was x cubed plus 2x squared plus... No, I think it was 3x squared, right? Yeah, 3x squared plus 2x. And so immediately I can see, well, an x factors out of the bottom. And I've seen this one enough times to know this is x plus 1 times x plus 2. So it's almost this same telescoping sequence that I've known, and that's been a question I've known for years. We just have a third term. Okay, but how would that affect things? So here's what partial fractions are. They're useful if you go on and study more advanced calculus techniques. But I know, it's a high school contest. Why are you talking about calculus? I'm just saying this is where you can see this sort of a thing. But anytime you factor a rational polynomial like this, and you have just linear terms on the bottom, you can always find constant real numbers a, b, and c to make equality between this expression and this expression. We just have to actually reach out and figure out what are the a, b, and c. So this is called partial fractions. If you're interested in learning more, by all means look that up. But probably most of the results you will find will involve calculus and the telescoping sequences that I mentioned earlier. But it's useful for fancy math things like integration. So what do we do for something like this? How do we figure out what constants to use? Okay, and if you hadn't seen a question like this one before, or if you hadn't seen partial fractions before, not saying you had to see them from calculus or something, I could see you'd probably be quite lost with this question. Anyways, what I'm going to do is multiply by x times x plus 1 times x plus 2. And that'll leave me... I'll get rid of all the fractions, which is nice. There's x in there. X times c. So c x times x plus 1. Okay. Now, there's lots of ways we could do this. We could expand this side out and say, hey, it's a polynomial, and this is technically a polynomial, just a boring constant polynomial. And polynomials are only equal if their coefficients are equal. And so we could do that. But here's a trick that I like when doing partial fractions. And I pass this on to my calculus students, even though it's not strictly required. But what we've got over here is a polynomial, and this is a polynomial. So they should be equal no matter what numbers we plugged in. Now, you might say, 1, that's not a function. Yeah, it is. It's just a very boring function that if you hand it a number, it'll always spit out 1. So, for example, if I were to plug in the value 0 over here, 1 should be a times 0 plus 1 is 1, 0 plus 2 is 2, plus b times 0 times 2, plus c times 0 times 1. But now these go away, so 1 should be 2a. A should be a half. And we can do the same sort of thing. Pick another one, like negative 1, that's going to make these two terms 0, and leave the b stuff alone. Okay? So, we know what a is, but we don't really need it. Negative 1 plus 1, negative 1 plus 2. B times negative 1, what's negative 1 plus 2? It's 1. And then C times negative 1. And then, we get zeros here. So these go away, and so 1 is going to be negative B. So B is negative 1. And we can do the same thing, plug in x equals negative 2. Again, the left side should equal the right side no matter what value x is. And so we'll get negative 2 plus 1, and then negative 2 plus 2 is 0. B times negative 2, and then negative 2 plus 2, again 0. And then C will get negative 2, negative 2 plus 1 being negative 1. So we'll get 1 is 2c, so c is a half, just like a was. So what have we learned? Well, f of x, which looks like this, could actually be written as 1 over 2x plus, plus negative 1, so let's say minus 1 over x plus 1 plus 1 over 2 x plus 2. And you might say, okay, great, you've got a new form for f of x. How is that going to help? Well, let's write out the first few terms. F of 1, f of 2, f of 3, f of 4 even. So using this new form, we get 1 half minus 1 over 2, so that's x plus 1, plus 1 over 4, which is 2 times 2. And you know what, actually, I think I'm going to write it like this. 2 times 1, 2, and then 2 times... Oh, this should be 3. So it should be 6. Oh, I'm almost had a problem there. Okay, and then what else can we have? Well, the next one will be 1 over 2 times 2, minus 1 over the middle term 3, so this should be minus 1 over 4, this should be minus 1 over 5. And then plus 1 over 2 times 4, plus 1 over 2 times 5, plus 1 over 2 times 6. And so if we're adding all these up, take a look here. We get minus 1/3 and then plus a half a third plus a half a third. These cancel out. Same with these ones. These cancel out. And so if we kept going, what would be left over at the end? So if we... So notice, so sort of, we get half of a third plus another half of a third and then minus a full third. So that's why these sort of cancel out. Same with half a quarter, minus half a quarter, and then plus another half a quarter. Those cancel out and so on. So if we did this a little smaller, we had f of n minus 2, f of n minus 1, and f of n. And then maybe we'll add in another term as well. If we just kept adding up enough of these, what would we have? We'd have a half of 1 over 1 minus 1 over 2 plus a half of 1 over 3, half of 1 over 2, half of 1 over 3, half of 1 over 4, half of 1 over 4, half of 1 over 5, half of 1 over 6. I do apologize for the low resolution viewers because I am writing kind of small. Have minus a half of n minus 3, no, sorry, n minus 2, minus a half of n minus 1, minus a half of n, minus a half of n plus 1. Or not a half, minus just 1 over n plus 1. Plus 1 over 1 half 1 over n plus 2, 1 half 1 over n, 1 half over 1 over n minus 1, 1 half 1 over n minus 2, 1 half 1 over n minus 3. Let's just make sure we don't get confused here. Plus a half 1 over n minus 1, plus a half 1 over n, plus half 1 over n plus 1. But then look what happens. Diagonals sort of cancel out. And so similarly, we get a half of 1 over n minus 1, another half of 1 over n minus 1, so that gives me a full 1 over n minus 1, and then we subtract off a full 1 over n minus 1. Same thing with these 1 over n's. So everything sort of cancels out other than this first sort of triangle of 3 terms and this triangle of 3 terms. So if n is big enough, this is all that's going to be left. Everything in the middle cancels out. So we get this nice cancellation effect, just like with telescoping sequences, and what's left, we get a half minus another half, that's the first row, plus a half-half, so plus a quarter, and then plus 1 over 2 times n plus 1, minus 1 over n plus 1. Then plus 1 half n plus 2. So those cancel. Part of that will cancel, so we'll get 1 quarter. So a half 1 over n plus 1 minus a full 1 over n plus 1 should be minus a half n plus 1, and then plus 2 n plus 2. So we can simplify this as well. We can say, oh, and there's that quarter we had. So maybe we don't want to simplify all of these. Maybe we just want to simplify and get a nice common denominator by multiplying top and bottom by n plus 2, and then n plus 1. So this will be 1 quarter plus n plus 1 minus n plus 2, all over 2 n plus 1 n plus 2. So this will be part of that goes away. We're left with a minus 1. So 1/4 minus 1 over 2 n plus 1 n plus 2. And I want this to be bigger than 503 over, I think it was 2004. It's the year of the contest, right? Yeah, 503, 2014, which itself is... Oh, rats! This is you can't get a quarter of 2014. But we could say 1/4 minus 503 over 2014 has to be greater than 1 over 2 n plus 1 n plus 2. And we could multiply 1006, 4028, 1007, 4028, which is really just 1 over 4028, has to be greater than 2 n plus 1 n plus 2. And so 2 n plus 1 n plus 2 has to be greater than 4028. Divide by 2 on both sides, 2014 there. So I guess we could say n squared plus 3n plus 2 needs to be greater than 2014. I suppose we could find roots, but this is a short answer question. So we don't need to show our work. We could just guess and check our way to an answer. Or we could say, well, what do we want? We want the smallest positive integer n, so if we could get close. What's close? Well, n plus 1 squared being greater than 2014 would definitely do it, because we're multiplying by a bigger number than just another n plus 1. What's the smallest square greater than 2014? 45 squared is 2024, so n equals 44 will work. Could something smaller, could n equals 43 work? So we'd be looking at 44 times 45. Is that bigger than 2014? So that'll be 180, 180. So 0, 8. So 1980, no it won't, but 45 times 46 will work. Because that would be... 6 times 45 would be 270, and then 180. 0, 7, 0. Wait, what? How is that bigger? It's not. So... Oh, right, because I was saying 45 squared should be smaller than that. So, okay, yeah. So 43 won't work. 44 clearly does work. So n equals 44 is smallest. And that's all we really need. But we've shown our work just in case. And so I can't remember. It's 2000. Yeah. So we would just say 44 and get all the marks. But if we did something wrong, we've at least shown our work, how telescoping sequences work. Partial fractions are an interesting thing to look into, especially with telescoping sequences like this one. And the simple example I mentioned earlier. So they're things to look into if you haven't seen them before. But I think I'm ready to move on to Part C of the contest, so I will see you for more of the 2014 paper in the next video.